the inequality of Clausius. The first step in our consideration of property we call entropy. As property. Is to establish the inequality of Clausius. The inequality of Clausius is a corollary or a consequence of second law of thermodynamics. Is a consequence of thermodynamics. It will be demonstrated to be valid for all possible cycles. For all possible of cycles, all possible cycles, including both reversible and irreversible heat engine and refrigerator. Both reversible and irreversible heat engines and refrigerator. Since any reversible cycle can be represented by a series of Carnot cycles, any cycle can be represented by a series of Carnot cycles. In this analysis, we need consider only a Carnot cycle that leads to inequality of Clausius. Consider a cycle only a Carnot cycle that leads to the inequality to the Clausius. Consider first a reversible Carnot heat engine cycles operating between Consider heat engine, Carnot cycle, heat engine and Carnot cycle that operate between TH and TL. So consider this picture for an example. Consider this picture, the cyclic integral of the heat transfer for the Carnot cycle. We have QH minus QL, because we have a reversible work which is greater than 0. Since TH and TL are constant, from the definition of the absolute temperature scale and from the fact that definition of the absolute temperature scale and from the fact that this is a reversible cycle, we have these relations. QH on TH minus QL on TL equals to 0. On TL so in this case, if the cyclic integral of the heat, the cyclic integral of the delta Q approaches 0 and the cycle remains reversible, the cyclic integral of zero and the cycle remain reversible. The cyclic integral of remains 0 Thus, we conclude that for our reversible heat engine, and due to the it is because we have net output work, because we have from the temperature scale, thermodynamic temperature scale, absolute temperature scale. And also reversible cycle. Now consider an irreversible cycle. Heat engine operating between the same TH and TL. Irreversible cycle between TH and TL at operating temperature. Comparing an irreversible process with the reversible process, we have W reversible greater than W irreversible. W was defined as QH minus QL for reversible greater than QH minus QL for irreversible. Consequently, in this case, because we have same QH minus QL reversible greater than QH minus QL irreversible, we can obtain that QL reversible irreversible. Yes, because we have a minus sign here, multiplying to minus, we change the QL reversible. It is obvious because we have the greater efficiency irreversible engines. Consequently, we can also have the, because of net output work, QL irreversible greater than 0, and also we have this relation delta Q on T QH on TH minus QL irreversible on TL for this expression for the real irreversible on TL. This is come from this fact it is smaller than 0. From this fact that for the absolute temperature scale we have this relation QL on TL, and because QL irreversible greater than QL reversible, we can calculate that QL irreversible on TL greater than QL reversible on TL, which is equals to QH on TH. So we can calculate that QL irreversible on TL greater than QH on TH. As a result, QH on TH minus QL irreversible on TL smaller than 0. So for any irreversible process we have these two relations. Greater than 0 equals to QH QL community that also have, because the engine to become more and more irreversible but keep QH, TH and TL fixed, the cycle integral of delta Q then approaches 0, and that for delta Q on T becomes a progressively large negative value. In the limit as the work output, we can have this relation for any irreversible heat engine. To complete the demonstration of inequality of Clausius, we must perform similar analysis for both reversible and irreversible refrigeration cycle. For the reversible refrigeration cycle, reversible refrigeration cycle, we have and because in the refrigerator we have the work input and heat from QL, and work is QL minus QH. As a positive sign, what a cycle is integral of delta Q approaches to 0 . Zero reversibly, the cyclic integral of remains 0 also. And for a reversible process due to the absolute temperature scale, we have this relation. For our reversible refrigeration cycle, we have equals to 0. Finally, let an irreversible cyclic refrigerator operate between temperatures TH and TL, receive the same amount of QL as irreversible refrigerator. Operate between TH and TL and receive the same amount of heat QL as we know QH minus QL is W. We need the W irreversible greater than W reversible due to the inequality, and the irreversible minus QL greater than QH minus QL. As a result, we have QH reversible. That is, the heat rejected by the irreversible refrigerator to the high temperature reservoir is greater than the heat rejected by the reversible refrigerator. Therefore, for the irreversible refrigerator, we have also the work plus QL input work and is smaller than 0, and for minus QH irreversible on TH plus QL TL smaller than 0. As we make these machines progressively more irreversible, but QL, TH and TL and TL constant, the cyclic integral of delta Q and delta Q on T for all irreversible refrigeration cycles are and for also smaller than 0. Summarizing, we note that in regard to the sign of delta Q, we have considered all possible reversible cycles, and for each of these reversible cycles we have also considered all possible irreversible cycles for the sign of integral of delta Q, and for all these irreversible cycles we have this relation. Smaller than 0. For all cyclic we can result for all cycle we have on T where inequality holds for reversible cycle and the inequality for reversible cycle. This relation is known as inequality of Clausius. The significance of the inequality of Clausius may be illustrated by considering the simple steam power plant cycle as shown in this picture. This cycle is slightly different from the usual cycle for a steam power plant in that the pumps handle a mix of liquid and vapor in such proportions that saturated liquids leave the pumps and enter the boiler. Suppose that someone reports that the pressure at quality and quality at various points in the cycle are as given in the picture. For example, 90% quality and pressure, and in point 4 we have quality of 10%, saturated with 100, and saturated liquid 0% gas liquid. Does this cycle satisfy inequality of Clausius? Does this cycle satisfy the inequality of Clausius? Heat is transferred in two places, the boiler and the condenser. Heat boiler condenser. Since the temperature remains constant in both the boiler and condenser, this may be as this expression. T3. So we have for this because we had heat transfer in boiler and condenser, we have this relation on the T1, 3 to 4 at T3. Constant temperature and constant temperature boiler, constant temperature condenser. Let us consider 1 kilogram. As the working fluid, we have then for this special case P equals to 50 kilograms can be calculated at temperature saturated pressure equals to 50 kilopascal. We have 10 quality and 90% quality here, and HA from the table. Anyway, Q from 3 to 4 also saturated vapor minus saturated liquid minus saturated vapor condition. This part, and for the 3 and 4, 90% and 10% quality with pressure equals to 50 kilopascals. From the tables we can calculate at temperature equals to the saturated temperature can be extracted from the table A, B2, B1. Kilogram Kelvin. So we have satisfied the inequality of Clausius.